Morning student. I am Professor NKH. Today I am taking module 2, which is related to instruction and programming. Then first we are discussing about, I am the Professor NKH from Hirasugar Institute of Technology. Today I am going to deal some related to the ARM programming using assembly language. So, for example, you can consider swapping of two instructions, swapping of two numbers in a register, swapping the register contents. Simply, for example, you can take a register 1, you can store some number, and register 2, you can take another number. You can interchange the content of register 1 into another. This is known as swapping of register contents. So I am writing a simple coding techniques in ARM programming. Let us consider a program. You can declare the area, program 3 and code read only. These are you can declared earlier. Then ARM processor will be able to understand about this type of coding technique you should be utilized. So you should be declared it, then only ARM processor is understood. So first of all you can load a number. Number may be anything else. Then load the register R0 into F63104C. Load some data. Here we are giving some specific address and load any data that is present in R0. And similarly you can load another data in the register R1. So 0 into you can allocate some numbers, we are specified some locations, load another data. What you will do, for example in R0 number 10 is there, in R1 11 is there. So if you want to exchange or interchange, swap these numbers, whatever the content of R0 which is to be transferred in R1, then similarly vice versa. So these two things takes place with the help of XOR operation. So XOR operation, exclusive OR operation, which is does XOR R0, R0, whatever the content of R1 that's to be transferred in R0 register. Then you can do the XOR operation R0 XOR R1. Similarly, in the second data, XOR R1, R0 R1, then R1 XOR to whatever the content that is to be transferred in R1. So similarly R0, R0, R1, that the data is transferred into another register. So the swapping operation is completed, then stop, B stop, that is the instructions provided by ARM processor. Then stop program and of this program. So in this way you have to be swap any two numbers, any two contents from one register into another register. These are the type simple programming techniques in ARM programming language. So in we are entered to another interesting part in hardware architecture, the structure of ARM assembly module. The structure of ARM assembly module, it contains a language module has several constituent parts. These are ELF section, means area directive. I already told they declare the areas. Then application entry directive. Then application execution. Then application termination. So program end directive. These are the important steps writing the assembly, ARM assembly coding techniques. So application entry means the entry directive declares an entry point to the program. It marks the first instructions to be executed. Then application execution, then the process label and it's load the decimal values 10 to 3 into register R0 and R1. These registers are added together and results placed in R0. So application termination, after executing the main code, the application terminates by executing software interrupt instructions to all interrupt service routine. Then program end. The end directive instruct the assembler to stop processing the source file Every assembly language source module must finish with an end directive on line by itself. Any lines following the end directive are ignored by the assembler. Then another important technique in ARM processor is layout of ELP. General layout of assembly program in general form of lines. Label we can provide the specific space. Each field must be separated by one or more white space. Then actual instructions never start in the first column since they must be preceded by white space even if there is no label. All three sections are optional and assembler will also accept blank lines to improve the clarity of the code. Then next we are proceeding the another important step is assembler directives. There are some instructions in the assembly language program which are not a part of processor instruction set. These instructions are instructions to the assembler, linker and loader. These are referred to as pseudo operations or assembler directives. The assembler directives enable we to control the way in which the program assembles then and list. They act during the assembly of a program and do not generate any executable machine code. Area directive instructs the assembler to assemble the new code or data. And entry operation, what it does, the entry directive declares an entry point to a program. And the end directive informs the assembler that it has reached the end of a source file. Space or fill. The space directive reserves a zeroed block of memory. The fill directives reserves a block of memory to fill with a given value. DCB means DCB directive allocates one or more bytes of the memory and defines the initial runtime contents of the memory. Then DCD or DCDU. DCD directive allocates one or more words of memory aligned on 4-byte boundaries and defines the initial runtime contents of the memory. Is same except that memory alignment is arbitrary. Then DCW is directive allocates one or more half word of memory aligned on 2-byte boundaries and defines the initial runtime contents of the memory. Then DCI, the DCI directive allocates 2 or more bytes aligned memory and defines the initial runtime content of the memory. These are the assembly directives. Then we are proceeding to the next, that converting C function into assembly language. That is, the conversion is most important from one language into another language. So the conversions which takes place, the section of C function by an assembly function and how to optimize it for performance. Let us see some examples showing how the assembly it is to be converted. Then in step 1, remove the C definitions of whatever the declarations. Then as produce a new C file main1.c. Then step 2, add an ARMS assembler file. For example, square of that numbers with the following contents: area, text, and read only. You can export values you have to be entered. The area directive names the area code sections. That code lives in the word next to area is a area name. If we non-alphanumeric characters as the area name, then we have to enclose the name in vertical bars as indicated in the above code. Here in the first line code we defines read only code area. And one more point we are writing here, export directive makes the symbol square available for external linking. The third line we define that symbol square as code label. It is important note that the ARM treats a non-intent text as a label definitions. So return value is return the register 0. End directive marks the end of assembly file. Comments follow a semicolon. We can build above examples by executing these process. Then converting entire program including main into assembly language. Here also we can follow the certain steps while writing the programs. Here we can use the import these values. Import directive is used to declare symbols that are defined in other files. The imported symbols library $request makes a request, will write it in programs, request that the linker links with the standard ARM C library. The weak specifier prevents the linker from giving an error. If the symbol is not found at the link time, the symbol is not found, it will take the value 0. The second imported symbol main is the start of the C library initialization code. Importing printf allows to call that C library function. The RL directive allows us to use name for registers. In this case, we define I as a alternate name for register R4. Using register names makes the code more readable. It is also easier to change the allocation of variable to register at the later stage. On some procedure called standard states that the function must preserve register R4 to R11 and SP in our code we corrupt, and calling the printf will corrupt. So these are the proceeding steps while converting entire program into assembly language. Then another important technique is profiling and cycle counting. So in profiling, the first task in optimizing the performance of subroutine or subprograms or functions is to identify the critical routines and measures their current performance. This task can be accomplished with the help of profiler and cycle counter. Then profiler, what it does, it is a tool that measures that proportion of time or processing cycles spent in each subroutine. Then cycle counter, it measures the number of cycles taken by specific routine. Then after optimization, we can measure the performance improvement by using a cycle counter to benchmark a given subroutine before and after an optimization. The ARM profiler works by sampling the program counter PC at resume intervals. The profile identifies the function the PC points to and updates a hit counter for each function it encounters. Another approach is to use the traceout of a similar as source for analysis. To provide good results, PC sample profiler has to take enough samples. We can even implement PC sample profiler in a hardware system using timer interrupts to collect the PC data points. However, the timer interrupts will slow down. ARM implementations do not normally contain cycle counting hardware. In such case, we can use ARM debugger with ARM simulator to measure cycle counters. And another important point we are going to discuss about the pipeline hazards. There are situations called hazards that prevent the next instruction in the instruction stream from being executing during its designated clock cycles. Hazards reduce the performance from the ideal speedup gained by the pipelining. There are three classes of pipeline hazards. First one is structural hazards. They arise from resource conflict when the hardware cannot support all possible combinations of instructions in simultaneous overlapped execution. And second is data hazards. They arise when an instruction depends on the result of a previous instruction in a way that is exposed by overlapping of instructions in the pipeline. Then third one is control hazards. They arise from pipelining of branches and other instructions that change the PC. Then hazards in pipelines can make it necessary to stall the pipeline. Pipeline interlock. It means whenever there is a hazard, it stalls the processor, which brings down pipeline efficiency. This is known as pipeline hazards. Then we are proceeding instruction scheduling. Instruction scheduling, we are already familiar about whatever the each instruction which is to be declared, how much time it is taking. This is known as instruction scheduling. Instruction scheduling, there are different types of load scheduling are there. Load scheduling by preloading. It loads the data required for loop at the end of the previous loop rather than at the beginning of the current loop. Since loop I is loading data for I plus 1, there is always a problem with the first and last loops. For the first loop, insert an extra load outside the loop. For the last loop, be careful not to read any data. This can be effectively done by conditional execution. Similarly, load scheduling by unrolling. Here we perform multiple loops together and the result of an operations from loop I is not ready. We can perform an operation from I plus 1 that avoids waiting for the loop I result. This method of load scheduling works by unrolling and then interleaving the body of the loop. Then another important point is register allocation. We can use 14 of 16 visible ARM registers to hold general purpose data. The other two registers are stack pointer R13 and program counter R15. For a function to be ARM thumb procedures called standard compliant, it must preserve the Kali values of register R4 to R11. The stack should be 8 byte aligned. We can use the following templates for optimize the assembly routine requiring many registers. To keep the stack 8 byte aligned, we need to stack R12. We need not stack R12 if your routine does not call other ATPCS routine. For ARM V5 and above, we can use the preceding templates. For ARM V4 below, we need to add the following line of the code at the end of the above templates. So allocating the variable, next point is allocating the variable to register number. When we write an assembly routine, it is recommended to use name for the variables rather than explicit register numbers. Reason for this is this allows us to change the allocation of variable to register number easily. We can even use different register names for same physical register number when their use does not overlap. Register names increase the clarity and readability of optimized code. We can also swap all occurrence of two registers RA and RB in a routine. The function of routine does not change. However, there are some cases where the physical number of register is important. Argument registers. In a ATPCS convention defines that first 4 arguments to a function are placed in register R0 to R3. Further arguments are placed on the stack. The return value must be placed in R0. Then register used in a load or store multiple. Load and store multiple instructions, LDM and STM operate on list of registers in order of ascending register numbers. If R0 and R1 appears in the register list, then processor will always load and store R0 using a lower address than R1 and so on. Load and store double word, the LDRD and STRD instructions operate on a pair of register with sequential register numbers RD and RD plus 1. Furthermore, RD must be even register number. Let us see how to allocate registers when writing assembly. Suppose we want to shift an array of n bits upwards in memory by k bits. For simplicity, we assume that n is large and multiple of 256. Also assume that 0 less than k and less than 32 and that the input and output pointers are word aligned. The C routine shifts bit is as follows. Then conditional execution. Conditional executions, which is to be by combining conditional execution and conditional setting of flags, you can implement simple if statement without any need of branches. This improves the efficiency since branches can take many cycles and also reduce the code size. Let us see so many examples. You can use it in loop and conditional instructions. You have to be evaluated at that time. This is known as the conditional execution of any assembly level programs. So in this way we can summarize this module 2 part B. So it ends.